In 2019, radio astronomer Anna Kapinska encountered an image of an enormous, enigmatic object situated billions of years from our planet, deep within cosmic space. Her reported label for the file conveyed the profound mystery of what she was seeing. What the fuck? The object resembled a ghostly, circular wisp of smoke, an unusual glowing structure of radio waves that did not correspond to any known celestial phenomenon, such as a supernova remnant or a galactic collision. A fundamental question arose: what in the universe could possibly create such a thing? While this particular object was strange, it turned out not to be unique. These formations have since been named odd radio circles, or ORCs, and they seem to embody many of the unexplained aspects of the cosmos. Since Kapinska's initial observation, 5 ORCs have been officially confirmed, with several other similar shapes potentially matching the same classification. A profound puzzle remains regarding the cosmic power capable of forging a ring of energy a million light-years in diameter, a structure so vast it surpasses the size of our Milky Way by a factor of 10. Astronomers wonder if these radio circles represent the remnants of galactic renewal, or perhaps the fading echoes of a process we have yet to understand. Another intriguing question is why so few of them have been detected. This entire mystery began to unfold thanks to significant progress in modern technology. Around the beginning of the new millennium, advancements in radio astronomy led to a dramatic expansion in the catalogue of known radio sources, growing from a few 100,000 to several million. For many decades prior, this number had remained largely static. That changed only recently, as the field of radio astronomy was poised for another major leap forward. Australia's National Science Agency, the Commonwealth Scientific and Industrial Research Organisation, managed the deployment of the groundbreaking Australian Square Kilometre Array Pathfinder Telescope, or ASCAP. This was one of several new radio observatories coming online during that period. The Western Australia facility is distinguished by its 36 radio dishes, each measuring 12 metres across, but what truly sets it apart is its phased array feed technology. This innovation permits the telescope to image immense sections of the sky simultaneously. Unlike its predecessors, ASCAP possesses a remarkable field of view, spanning 30 square degrees. This area is comparable to the celestial footprint of about 150 full moons, as observed from Earth. The phased array feed also gives astronomers the ability to filter out interfering radio signals from sources like satellites, which could otherwise create blind spots for the telescope's sensitive receivers. With this new generation of instruments, radio astronomers gained the capacity to perceive even very faint and diffuse celestial objects. Professor Ray Norris of Western Sydney University and CSIRO, who would later be a key figure in the original ORC discovery, had predicted something extraordinary. He anticipated that the Australian telescope's evolutionary map of the universe project, known as AMU, would contribute to a massive increase in our knowledge of radio sources throughout the cosmos. The project's name is a tribute to the emu in the sky, a constellation recognized for generations in Aboriginal astronomy, which is formed from dark nebulae within the Milky Way galaxy, rather than from stars. The total number of radio sources found by all radio telescopes in history up to that point was approximately 2.5 million. The EMU project alone was projected to elevate that figure to an astonishing 70 million radio sources. It is important to remember that this estimate represented the expected discoveries from just one of these new advanced telescopes. Norris was confident that this flood of new data would reveal some significant surprises, and it did, much more quickly than anyone had anticipated. The EMU project surveyed large swaths of the sky that had not been previously imaged by other telescopes, compiling immense catalogues of information. The sheer volume of data was so great that scientists assumed they would need the assistance of machine learning algorithms to analyze it all. However, it was during a manual review of some of the project's early images that Anna Kapinska, the radio astronomer who found the first ORC, noticed the strangely shaped radio emissions with her own human eyes. This detail seems to make the discovery even more compelling. It serves as a powerful reminder that even in an era of big data and sophisticated machine learning, human curiosity remains an essential component of the scientific method. While examining these initial EMU images, Kapinska began to see some peculiar shapes that she could not classify as any known type of object in space. On one image of these odd forms, which showed a circle of radio emissions like a giant smoke ring adrift in the distant universe, she inscribed the label, "What the fuck?" perfectly capturing the baffling nature of the finding. Kapinska had never witnessed anything remotely like it before. After she shared her unusual discovery with her colleagues, a team of radio astronomers that included Norris and Emil Lenk started to meticulously search through the images for more of these circular radio objects. Lenk located a second one just a few days after the first was identified, and the team ultimately decided on the name Odd Radio Circles. Initially, they were not even certain if these were genuine celestial objects or simply some form of instrumental error or imaging artifact from the telescope. They were, however, able to use other telescopes to observe the ORCs, which provided confirmation that these strange radio circles were indeed real. The immediate question that followed this confirmation was, naturally, what are these things? Fortunately, our understanding of ORCs has grown since Kapinska first identified one. An image of ORC-1 from the EMU pilot survey shows a blurry, grayscale shape. The EMU team also created a second, colorized and enhanced version of the image, which helps to reveal its less apparent features while preserving the original resolution. In this color image, ORC-1 is depicted as a hazy, greenish-blue circle. Since this ethereal object is only visible in radio wavelengths, the color was added artificially to help us visualize its structure. This enhancement also allows us to discern more distinct characteristics within the ORC, which is located at least 1 billion light-years away in deep space. Early calculations proposed that ORC-1 might have a diameter of around 1 million light-years. More recent observations, however, suggest its width could be as much as 2 million light-years across. This would make it 20 times wider than our own galaxy. So we have a sense of their immense size and great distance, but their fundamental nature remains a mystery. At first, it was suggested that these unusual rings could be the remnants of a powerful supernova, but the circumstances did not align with this theory. For one thing, supernova remnants are typically found near the plane of a galaxy, and all of the identified ORCs are located too far away from any such plane. A further compelling detail is that some of these ORCs seem to contain galaxies at their centers, a characteristic not found in supernova remnants. What also stands out is that the sense of scale is entirely different. While most supernova remnants measure only a few dozen light-years across, these radio rings are vastly larger, expansive enough to encompass entire galaxies within their core. The ORCs observed to date have diameters ranging from hundreds of thousands up to 2 million light-years, confirming that they cannot be supernova remnants. These objects must represent something else entirely. One possibility is that ORCs are a phenomenon we are already acquainted with, such as the jets emanating from a radio galaxy, but their true nature is obscured by immense distance or perhaps an unusual viewing angle. Since the initial finding of ORC-1, astronomers have had opportunities to study it with other telescopes, which have uncovered an object at the circle's center visible in both optical and infrared light. Using the South African Meerkat radio telescope, an array of 64 interconnected dishes, Norris and his team gathered data on ORC-1 for 10 hours to construct a detailed image of the circle. They then superimposed that radio map onto optical data from the Dark Energy Survey, which revealed an elliptical galaxy situated in the middle of the ORC. This crucial information allowed them to calculate the central galaxy's distance from Earth, estimating it to be approximately 5 billion light-years away. The team not only identified this central elliptical galaxy, but the high-sensitivity imaging also exposed a complex inner structure of knots and arcs, with additional galaxies located at these points of brightness. If Norris and his team's assessment is correct that this elliptical galaxy is truly near the heart of ORC-1, it likely played a role in the radio circle's formation. It remains possible, however, that the galaxy's position is merely a line-of-sight coincidence, appearing near the ORC's center from our perspective without being physically associated. Armed with this new imagery and data, the team outlined 3 potential origin stories for the ORC in their 2022 paper, with the evidence not strongly favoring one hypothesis over the others. The first scenario considered was that ORC-1's spherical shell is the aftermath of a cataclysmic event within the host galaxy, such as the merger of 2 supermassive black holes. In this model, Such a merger would unleash a powerful shockwave in all directions, accelerating electrons throughout the intergalactic medium. This process could inflate a bubble of radio emissions that would appear to us as a circle with a brightened outer edge or ring. For this to be the case, the ORC would be expected to harbour a supermassive black hole or an active galactic nucleus. Intriguingly, ORC-1 does show signs of a radio-loud galactic nucleus, just as this hypothesis would predict, and so do two other observed ORCs, lending this idea further credibility. A second possibility put forth by Norris and his team for ORC-1's origin is that it might simply be the radio jets from a radio-loud active galactic nucleus, or AGN, viewed directly end-on. Radio AGNs are a class of galaxy that expels enormous amounts of energy from their core in the form of two plasma jets, powered by matter spiraling into a central supermassive black hole. As noted, we already know that AGNs are present in many of the ORCs that have been studied so far. If such a system were oriented with its jets pointing toward Earth, the two lobes of radio emission would be superimposed, creating the very appearance we see with ORC-1, a ring-like structure with a host galaxy at its center. Still, three-dimensional simulations are required to determine if these specific AGNs are indeed producing radio jets, and, if they are, whether we are truly observing them head-on. The third and final hypothesis for an origin story suggests the radio circle of ORC-1 is caused by a phenomenon known as a starburst termination shock. In this explanation, millions of stars would have been created during a brief but intense period of star formation inside the elliptical host galaxy. Throughout this phase, new stars would have formed at a rate far exceeding the norm, a period lasting for only a few tens of millions of years, which is just a flicker on cosmic timescales. These stars would have generated powerful stellar winds, expanding out into space over billions of years, exciting electrons and creating a spherical bubble of radio emission, just like the one seen in ORC-1. Although the team modelled this possibility in greater detail than the other two hypotheses, demonstrating its mathematical plausibility, Norris was clear that the data did not favour this explanation over the others. So, despite having several compelling ideas, the origin of ORC-1 remains as enigmatic as the odd radio circle itself. As each new ORC has been discovered, the only thing that seems certain is that they are not all created in the same way. The name odd radio circles is, after all, intended as a descriptive umbrella term for any strange radio circle that cannot be explained by any known type of object. Therefore, while all ORCs share this common feature, each individual one may possess its own unique origin story. The discovery of ORC-2 and ORC-3, the second and third such objects to be identified, did little to resolve the mystery of their creation. In fact, their existence introduced even more questions. When viewed in this grayscale image, the two ORCs appear to be extremely close to one another, almost touching. They are of a comparable size, but on the right side of the frame, ORC-2 is bright and distinctly ring-shaped, whereas ORC-3, to its left, is faint and appears more like a solid disk. Indeed, ORC-3 might not even be recognizable in the grayscale EMU image, if not for the light grey speckles that seem to coalesce into a circular form right beside the more defined ring of ORC-2. Now, consider this colour image of ORC-2 and ORC-3. Here, the diffuse radio emission has been enhanced in red and overlaid on the original radio data shown in green. You can perceive the obscured green colour behind the red glow where the ring structure of ORC-2 is located. To the left, its fainter companion, ORC-3, is visible only in the diffuse red light. The proximity of these ORCs strongly suggests they are related in some way. But if that is true, why do they look so profoundly different? As much as one would hope to report a solution to this curious case of ORC-2 and ORC-3, since their discovery was published in 2021, the true nature of these sister circles remains an unsolved mystery to this day. Before delving into the origins of ORC-4, it is important to consider another discovery, ORC-5, which was identified in 2021 using data from the Australian Square Kilometre Array Pathfinder. While no dominant theory exists for this specific object, what stands out is that ORC-5, much like ORCs 1 and 4, possesses a central elliptical galaxy, An intriguing detail is that ORC-5 was uniquely observed to have not only this central galaxy, but also a nearby companion galaxy, at roughly the same distance from the radio ring. This proximity strongly suggests the two galaxies are engaged in a gravitational interaction. Although certain characteristics may repeat across the confirmed odd radio circles, it appears each one maintains its own distinct qualities. As more of these objects are discovered and confirmed, this pattern of individuality might change. However, with such a small number of examples and limited observational evidence, scientists have found it challenging to settle on a single origin theory. This brings the focus to ORC-4, nicknamed the Cloverleaf ORC, for its irregular shape, which proved to be yet another singular case. First located in archival data from the Giant Microwave Radio Telescope, the Cloverleaf ORC has become the most thoroughly observed and imaged of all these objects to date, studied across radio, X-ray, and visible wavelengths. In a stunning composite image of the Cloverleaf, data from several observations are combined, with radio emissions appearing in red, optical light shown in white to yellow, and X-ray emissions rendered in blue. This particular ORC is situated approximately 600 million light-years from Earth and has a vast expanse of more than 325,000 light-years, making it over 3 times the diameter of our own galaxy. In 2024, astronomers using the W.M. Keck Observatory in Hawaii detected a powerful fluorescent glow from oxygen atoms originating from the Cloverleaf ORC, a light that stretched across 130,000 light-years of its massive structure. This oxygen 2 nebula of heated, compressed gas, also known as shocked gas, seemed to be the product of a high-velocity explosion. According to Alison Coyle, an astronomer and astrophysicist at the University of California, San Diego, who led the research, this finding pointed to a compelling possibility. Since the Cloverleaf ORC also contains a central elliptical galaxy, Coyle's team suggested it could have been formed by a starburst termination shock event, which was one of the 3 primary hypotheses proposed for the origin of ORC-1. The researchers calculated the age of the stars within the Cloverleaf central galaxy, determining them to be 6 billion years old. Using this information, they ran a simulation demonstrating how a structure similar to the Cloverleaf could be created by a starburst that generated a high-mass outflow. In this scenario, the shockwave from a multitude of combined supernova explosions could have propelled both the sphere of radio emissions and the nebula of gas outward from the central galaxy. While this is an exciting explanation, particularly given its connection to an existing hypothesis for ORC-1, it is not the only one. In that same year, another team led by scientists at Germany's Max Planck Institute for Extraterrestrial Physics used the European Space Agency's XMM Newton X-ray telescope to make a different discovery. They detected diffuse X-ray emissions from within the Cloverleaf ORC, a first for any odd radio circle. Based on these observations, the team, headed by astrophysicists Bulbul and Chang, proposed that the Cloverleaf might be linked to a cosmic dance between 2 separate groups of galaxies. The X-ray data suggests the ORC could be the aftermath of a chaotic merger between 2 galaxy groups that were drawn together by gravity. Such a merger could have generated enormous shockwaves, leaving behind a gigantic bubble of radio emissions like the one observed. A significant question remains, however, as it is unclear why this specific merger of galactic groups would produce such an object when other similar mergers seemingly do not. As these competing theories illustrate, the mystery of how ORCs are formed is far from being solved. In fact, there is still debate over whether the Cloverleaf ORC is truly an ORC at all, as it appears more like a diffuse cloud and lacks the distinct, bright edges of radio emission that are considered a telltale feature. Researcher Norris has noted that other cloverleaf-shaped radio clouds have been seen in different galaxy groups, not all of which are associated with ORCs. The key to resolving which objects belong to the ORC family will be more data. Deeper observations in radio and X-ray frequencies could help identify more complex structures and allow astronomers to differentiate between genuine ORCs and similar-looking phenomena. Fortunately, several other candidate ORCs have been identified, and they may offer additional data for study and comparison against the known cases. The strange radio emissions that once prompted a "what the fuck" now have a proper name, but the jury is still out on their origins. Even so, projects like EMU and ASCAP are constantly providing new insights. While analyzing EMU data from a nearby dwarf galaxy, the Small Magellanic Cloud, astronomers found the ghostly remnants of two supernova explosions that were previously unknown to science, expanding our catalogue of celestial objects. In 2023, the EMU survey was also used to find another nearby supernova remnant, which turned out to be one of the closest to Earth at a distance of just 4,200 light-years. This remnant was measured to be about 130 light-years across and is thought to be only 13,000 years old. Beyond discovering supernova remains, the EMU project is also pioneering the use of machine learning and citizen science to identify and catalogue some 4 million radio sources through a project called the Radio Galaxy Zoo EMU, or RGZ-AMU. As of 2025, the project has enlisted over 2,000 volunteers who have helped classify more than 92,000 sources. Perhaps the most remarkable part is that anyone can participate in this citizen science project. To learn more, you can visit zooniverse.org and search for the Radio Galaxy Zoo EMU project. As our observational capabilities advance, it seems inevitable that astronomers will uncover more cosmic oddities, like the enigmatic odd radio circles, and perhaps even phenomena we have yet to imagine. Such discoveries hold the potential to illuminate not only the formation of these structures, but also the broader life cycles of galaxies, the consequences of intense starburst events, and the ways in which gas from ancient cosmic episodes can be traced far from its galactic origins. For the moment, however, the precise nature of these radio rings remains a subject of debate, with several compelling hypotheses under consideration. To solve this puzzle, scientists must engage in a form of cosmic archaeology on a scale that is difficult to fully comprehend. In 2022, a team using the Murchison Wide Field Array detected a peculiar new radio transmission, which repeated itself approximately every 22 minutes. Researchers were familiar with repeating signals of this kind, as they are the characteristic signature of pulsars. These are rotating neutron stars that sweep powerful beams of radiation across the cosmos, much like a lighthouse. But as the team delved into archival observation records, a surprising fact emerged. This particular signal had been reaching Earth with extraordinary regularity since at least 1988. Its stability was far greater than what would be expected from a pulsar with such a slow 22-minute rotation. If the source was a neutron star, it was a type never before encountered. The question then became, what was the origin of this persistent signal? This mystery challenges our fundamental understanding of some of the most extreme objects in the universe. The source, catalogued as GPMJ 183910, is situated at a distance of roughly 18,000 light-years from us. Its transmissions arrive in bursts that can last anywhere from 30 seconds to as long as 5 minutes. These pulses can appear at any point within a window of just over 6½ minutes, which itself is centered on the 22-minute mark following the previous pulse. To a casual observer, this might suggest a high degree of variability. The difference between a 30-second emission and a 5-minute one is significant, and an arrival time that can shift by more than 6 minutes does not immediately suggest a stable source. However, the physics governing neutron stars is incredibly complex. If the object is indeed a neutron star, a multitude of factors could influence the duration and timing of the pulses we detect. Despite these variations, astronomers successfully identified the signal buried within 35 years of data. Using this greatly expanded dataset, they were able to average out the short-term fluctuations. Their calculations confirmed a rotation period of once every 21 minutes and 58 seconds, and they also measured how much the object's spin had slowed over time. What they found was astonishing. The rotation period had remained virtually unchanged across the entire 35-year observation period. While it is expected that any such object would slow down as it radiates energy away, the data showed that if any deceleration occurred, it could not have lengthened the rotation period by more than 0.28 milliseconds. Had the change been any larger, their instruments would have detected it. This incredibly small value demonstrates that whatever this object is, it spins with a remarkable degree of consistency. For a typical pulsar, this level of stability would not be strange. Pulsars are often called the clocks of the cosmos, their mechanistic ticking so precise that they can be used as timekeeping references across immense cosmic distances. The strangeness here arises from the combination of high stability with an exceptionally slow rotation. To appreciate why this is so peculiar, it is helpful to review the mechanics of pulsars and the reasons they gradually lose rotational speed. Pulsars are a type of neutron star, which are the collapsed cores left behind by expired supergiant stars. Outside of black holes, they are the densest objects known to exist. A planet like Earth is composed of atoms that are more than 99.999% empty space, a result of the vast distances separating electrons from their incredibly dense nuclei. A neutron star, by contrast, is like a celestial body made entirely of the neutrons found within those nuclei. There are no electrons, no protons, and virtually no empty space. A single teaspoon of its substance would have a mass equivalent to 11 times that of the entire human population of 8 billion people. A standard neutron star packs about 35% more mass than our Sun into a sphere with a diameter roughly the length of Manhattan Island. To call such an object dense is a profound understatement. For reasons that are still not fully understood by astrophysicists, this extreme environment generates an immensely powerful magnetic field. The connection between this magnetic field and the signals we receive involves a complex process that generates the radio waves. It all begins with a single electron, which triggers an exponentially growing cascade of light and matter. Near the magnetic poles of the neutron star, the magnetic field can accelerate an electron, causing it to emit what is known as a curvature photon, which travels tangential to the magnetic field line. This event can be thought of as the beginning of a pulse. The curvature photon travels in a straight path until the angle between its trajectory and the magnetic field line becomes too large. Once a certain threshold angle is crossed, the photon's energy converts into matter, creating an electron and its antimatter counterpart, a positron, from the quantum field. This newly formed electron-positron pair possesses some momentum perpendicular to the magnetic field lines, which it immediately sheds by emitting synchrotron photons. Each of these two synchrotron photons can then, in turn, generate another electron-positron pair once they also cross the threshold angle relative to the magnetic field. This cycle repeats over and over, creating an exponential increase in the number of photons and electron-positron pairs. The cascade finally ceases when the synchrotron photons no longer possess sufficient energy to create new pairs. These remaining photons are what stream out into space, while the original electron continues its journey, creating more curvature photons and initiating further cascades. This pair production cascade explains why the light from a pulsar is so intense, allowing us to detect the signal from a tiny stellar remnant thousands of light years away. The reason we perceive this light as periodic pulses instead of a continuous glow is because the magnetic poles of a neutron star are almost never perfectly aligned with its rotational axis. It is much like the situation on Earth, where the magnetic north pole that a compass points to is not the same as the geographic north pole around which our planet spins. Pulsars are often imagined as immense cosmic lighthouses, sweeping concentrated beams of energy across space as they rotate. For a distant observer, such as one on Earth, these beams appear to flash past us repeatedly with each full rotation of the pulsar on its axis. These are the regular pulses of light that our instruments are able to register. It is important to note, however, that this is light with extremely long wavelengths, existing within the radio portion of the electromagnetic spectrum. This means that only a radio telescope is capable of detecting these emissions. The light that the generating cascade produces shares this same wavelength, with the peaks and troughs of its waves oscillating in perfect unison. A further defining characteristic is that the light waves are polarized, which signifies that they are all oriented along the very same axis. This particular quality is a known hallmark of neutron stars, and it is precisely what has been observed within the 22-minute signal. The signal also contains fluctuations that have a duration of between 0, 2, and 4 seconds, during which the axis of the light's polarization suddenly shifts by 90 degrees, becoming perpendicular to its original orientation before returning. This curious effect represents yet another signature of the cascades that occur at the poles of pulsars. With so much of the available data pointing toward a pulsar as the source, one might think the investigation would be a straightforward matter. Yet, a single variable mentioned earlier introduces significant doubt into this entire theory. The critical issue is the slow rotational rate of the neutron star, or more specifically, the combination of that slow rotation with the high stability of the source's spin. As pulsars emit their powerful beams into the cosmos, they lose energy, and the law of conservation of energy ensures that this causes the pulsar to slow down over time. Eventually, a pulsar's rotation will decrease so much that it can no longer supply the power for the pair production cascades, and its light emission begins to cease. At this point, the pulsar is said to have entered what is known as the death valley, a graph that plots neutron stars according to their rotation period on the x-axis, and the rate of change in that period on the y-axis illustrates this concept. The death valley is represented by a grey band running across the middle of the chart. Any pulsar whose properties place it below this line should no longer be shining like the bright beacons they typically are. What is remarkable is that our signal is positioned below even the lowest boundary marking the death valley, which implies that if this object were a pulsar, it should be thoroughly and completely switched off. And yet, we are clearly detecting it. Looking at the cluster of other known neutron stars on this graph reveals a typical spin rate of between 10 times a second and once every second. In stark contrast, our signal has a spin rate of only once every 1,318 seconds, making it over 1,000 times slower than a standard pulsar. This slowness would be plausible if the object were also slowing down very quickly, a characteristic that would move its data point upward on the graph, above the death valley. Such a rapid loss of energy would be sufficient to power the pair production cascade required to illuminate the neutron star's beacon. However, the neutron star is astonishingly stable, and its detection simply does not make sense under this model. The astronomers who discovered the signal explored an alternative mechanism that could potentially explain how a neutron star with these properties might have generated this light. Perhaps the object is a magnetar, which is a type of neutron star possessing an unusually powerful magnetic field, greater than 10,000 times the strength of the weakest neutron star magnetic fields. Magnetars are known to experience starquakes, which are cataclysmic events that release built-up tension in the upper crust of the neutron star. These powerful stresses are generated by the magnetar's intense magnetic fields and also by the gradual slowing of its rotation. A rapidly spinning magnetar will develop a bulge at its equator due to centrifugal force, distorting it from a perfect sphere. As the magnetar's spin decreases, its outer layers must readjust to a new equilibrium, shedding some of that bulge. The crust then snaps into a new position, causing a temporary realignment of magnetic fields and powering a release of energy as light that we can detect from Earth. The most powerful starquake ever detected, from SG 1806 20 inches 2004, released such a tremendous amount of energy that if it had occurred just 10 light-years from our planet, it would have triggered a mass extinction event. If any phenomenon could relight the beacon of a dead pulsar, it would be an event of this magnitude. So, could GPMJ 183910 be a magnetar that has undergone a starquake? And have we resolved the mystery of the 22-minute signal? It appears that this is not the case. We would expect these starquakes to also emit light in the X-ray part of the spectrum, but no X-rays have been detected from the source's position, which is roughly 18,000 light-years away. It is also inconsistent for a magnetar outburst to persist for 3 decades. A starquake is a temporary phenomenon, with its energy dissipating within a few years at most. It is simply incomprehensible that this signal could have existed for 35 years if it were indeed a magnetar. Once again, the signal's unique properties seem to exclude it from being a neutron star, even an exceptionally powerful one experiencing a special event like a starquake. But what other possibilities exist for the source of this mysterious signal? The astronomers who made the discovery proposed a few alternatives for the object's identity. One possibility is a highly magnetic white dwarf. A white dwarf is another kind of stellar remnant left behind after the recent death of a star, but one that lacks sufficient mass to collapse the empty space within its atoms and become a neutron star. A remnant of this type with an unusually strong magnetic field could potentially produce radio emissions. And since it is not a neutron star, it could plausibly have the slow and stable rotation observed in our object while still being active. The problem with this hypothesis is that it would necessitate an exceptionally strong magnetic field one greater than any we have ever spotted on a white dwarf. AR Scorpii is the only known radio pulsar that is actually a white dwarf, and its radio emissions are 1,000 times less luminous than the source of our 22-minute signal. If a white dwarf is an unlikely candidate, what other options remain? Astronomers have observed low-frequency radio waves originating from the interactions between stars and exoplanets, as well as from a binary system of two brown dwarfs orbiting each other. But this type of emission is typically weaker, around 100 million times weaker than the source of our signal. In the end, it seems that none of our current theories can adequately explain the 22-minute signal. While this unresolved question about the source might feel frustrating, this is precisely the kind of mystery that astrophysicists search for. When scientists encounter new data that challenges our long-held theories, these moments can usher in revolutions in our understanding of the universe that surrounds us. Our already tentative grasp of neutron stars is being fundamentally challenged. Astronomers feel confident that the relative ease of this signal's discovery suggests that many similar sources are waiting to be found within the galactic plane. Much like GPMJ 183910, these other signals could already be present in the data we have gathered. Identifying more of them would illuminate the processes that power emissions beyond the neutron star Death Valley. Whatever the mechanism is behind the 22-minute signal, it seems certain that we are on the verge of learning about an entirely new and previously unseen phenomenon. The Milky Way galaxy alone is thought to contain around 100 billion planets. Of this vast number, an estimated 30 million are believed to exist within Goldilocks zones, orbiting their stars at just the right distance to potentially support life. These worlds might also possess the necessary mix of chemical elements from which life similar to ours could emerge. Across the entire 13 billion-year history of the universe, if even a tiny fraction, just 1% of these planets went on to produce civilizations capable of reaching into the cosmos, then we ought to see evidence of thousands, if not millions, of alien races throughout our galaxy. This very line of reasoning led the Nobel Prize-winning physicist Enrico Fermi to formulate his famous Fermi paradox, which in essence asks, where is everyone? Here, we will explore some of the possible answers to this question, because while we do not know for certain if aliens exist, there are some surprising barriers that could prevent us from seeing them even if they do. Let's begin by addressing the most direct possibility. Perhaps there is no one out there to see. One consideration is that the emergence of life from non-living materials might be exceptionally difficult, or that the subsequent evolution of that life into an intelligent species like our own could be incredibly unlikely. If either is true, then it is entirely possible that no ships or signals populate the sky simply because there are no other aliens. We would be the first to have ever come this far. All other planets might be empty and desolate. It would then become our opportunity to spread out across the universe, discovering these uninhabited worlds. The only life we would ever encounter would be the life we carried with us from Earth. While this is a perfectly reasonable possibility, and there is no conclusive evidence to disprove it, this is not the only explanation for why the sky seems so quiet. We must also recognize that we are bound by a surprising natural limitation. For us to discover or establish contact with an alien civilization, one of two things must happen. Either we need to send a message to them and then receive a message in return, or an alien civilization must have made the first move by messaging us directly. There are different ways this could be accomplished. We might, for instance, send spaceships to one another, or perhaps use unmanned probes, but there are significant issues with any approach that involves more than just sending messages. Sending a spaceship is a complicated affair. At the speeds our current spacecraft can achieve, it would take an astronaut potentially millions of years to reach a destination. The Voyager 2 probe took approximately 49 years just to leave our heliosphere. The nearest star to us is 4 light-years away. In other words, it would take more than 81,000 years to get even that far, a span of about 2,700 human generations. And that scenario assumes that our closest cosmic neighbors are aliens. Even if we account for future technological improvements, it requires a colossal amount of energy to accelerate an object to near light speed. In fact, it would demand more energy than exists in the universe, as mass simply does not like to travel at those speeds. So, unless we or our alien friends are able to develop some kind of workaround, the most feasible way to communicate with other civilizations is to send them radio signals. In fairness, it is not implausible that this speed limitation will one day be surpassed. Scientists have hypothesized some promising ideas involving the movement of space itself within warp bubbles, rather than moving an object through space. The speed of light limit only applies to movement within a local area, so if your local area itself is in motion, you are fine. We actually have examples of this in nature around black holes. But until that becomes a scientific reality, we can proceed with the fact that it is much easier to call than to visit in person. It is significantly easier and cheaper to send out light or radio waves, a task as simple in principle as turning on a sufficiently large light bulb. So, let us assume that this is how our first contact with aliens will happen. Even in this case, however, we encounter a roadblock. Radio signals and light are more than capable of traveling at relativistic speeds. It is called the speed of light for a reason. Yet, that is its limit. Light speed, or just under 300 million meters per second. No signal can exceed that velocity. This, in turn, constrains how far we are able to see through space. Any signal from us would need to travel across the cosmos before reaching alien life. Then, even if they chose to respond immediately, their reply would need to travel all the way back. Let's imagine that happens. We only invented the radio in the mid-1890s, so we have not been able to do this for very long. As such, we would only have been able to exchange a message with aliens who lived at most 60 light years away from us. That is 60 years for a signal sent out in 1900 to reach the alien civilization, and another 60 years for it to come back. Our galaxy is roughly 100,000 light years across. Therefore, the 60 light-year bubble within which we could have communicated is truly tiny. In fairness, this limitation disappears if the aliens contact us first. After all, with the James Webb Space Telescope, we are now receiving light that has been traveling for 13 billion years from nearly the beginning of the universe. If an alien civilization came into being around 2 billion years ago and has continued to exist since then, that means they now have a 2 billion light-year bubble from which we could technically see them. A 10 billion-year-old civilization now has a 10 billion light-year bubble. However, a civilization located 10 billion light-years from Earth, having existed for only 9 billion years, would be entirely beyond our view. If we presume that such distant intelligences are out there, a fundamental question emerges. Why do we perceive no evidence of their presence? What has become of their potential signals? This entire line of reasoning, though, might be built upon a flawed premise, the idea that no transmissions from the stars have ever reached us. In truth, unusual signals have been detected. The challenge is that we remain uncertain of their origin. A fascinating case from history helps to illustrate this point. In 1961, researchers at The Ohio State University completed the construction of a specialized radio telescope, a remarkable instrument that was given the name Big Ear. Their work was part of a larger quest for evidence of extraterrestrial life, a detail worth noting as it introduces the possibility of confirmation bias in their interpretations. This massive installation, spanning the area of 3 football fields, operated on a principle similar to many modern telescopes. It was designed to gather incoming signals with a large primary mirror at one end, which would then bounce them towards smaller mirrors and ultimately into a pair of receivers at its core for processing. One might observe that the collecting dishes were not solid surfaces but rather wire meshes, which is a key detail. This is because Big Ear was a radio telescope, engineered not to capture visible light but rather radio frequencies. The specific design of Big Ear also meant its range of motion was more constrained than a conventional telescope that can pivot freely. The instrument's main reflector could only be tilted vertically, up and down, which restricted its listening window at any given moment to a very narrow band of the sky. This design was more affordable and simpler to engineer, and its creators devised an ingenious way to compensate for Big Ear's physical limitations. They oriented the telescope with such precision that the planet's own rotation would serve as its horizontal adjustment, turning it from left to right. By combining the Earth's steady turn with the reflector's vertical tilt, Big Ear could, with enough time, be aimed at any point in the celestial sphere. It was a rather clever solution to a significant engineering problem. The telescope's focus would sweep across the night sky in great, circular paths, listening intently for any anomalous signals for which there was no known natural cause, and then, In 1977, Big Ear detected something extraordinary. On August 15th of that year, a powerful pulse of radio waves arrived, lasting for 72 seconds. It was an astonishing 30 times stronger than the typical background static of the universe that Big Ear had ever registered. The signal was so profoundly different from the norm that the researcher who first saw the data famously wrote the word "wow" on the computer printout, giving the event its historic name, the WOW signal. What was particularly striking was its incredible uniformity. The signal's intensity rose, reached a distinct peak, and then subsided in a smooth, symmetrical arc, unlike the chaotic fluctuations one would expect from natural cosmic radiation. This suggested that its source was broadcasting with remarkable consistency, almost like the focused beam of a lighthouse sweeping past our planet as we turned to look and then turned away. Yet, it was not consistent in its reappearance. Because of Big Ear's design, the research team had to wait several minutes for the telescope's second receiver, its second ear, to pass over the exact patch of sky where the WOW signal had originated. When it did, the signal was gone. Since that day, despite numerous follow-up observations of that same region of space, the WOW signal has never been heard again. So, the mystery endures. What was it? Was it an instrument malfunction within Big Ear itself? Could a passing comet have generated a brief, anomalous emission? Or was it, perhaps, a genuine attempt at communication from an extraterrestrial civilization? The simple truth is that we do not have an answer. It remains entirely possible that the WOW signal has a perfectly natural explanation. A similar situation occurred when the regular, metronomic X-ray pulses from pulsars were first discovered. Some initially speculated they were alien transmissions before their true, natural origin was understood. It could be that we will one day detect another WOW signal and find that its source was not alien at all, but there is a crucial technical consideration that must be addressed here. If one were the lead scientist on such a project, the intuitive next step would be to point the telescope directly at the source of the WOW signal and wait patiently for a recurrence. To do otherwise would be to risk missing a follow-up transmission. However, the very way Big Ear was built made this impossible. Its movement was inextricably tied to the rotation of the Earth, which meant it physically could not remain fixed on a single point for more than a few moments. Consequently, we have no way of knowing if more signals arrived from that direction. It is conceivable that hundreds of additional transmissions, perhaps even an entire symphony of information, were broadcast over the next few hours. But because Big Ear was only listening to that spot for a fleeting instant each day, it would have only ever caught a single note. This situation highlights a deliberate strategic choice made by organizations like SETI, which are dedicated to the search for intelligent life. With limited resources and a vast cosmos to explore, they lack the time and funding to aim a telescope at one location for decades on the chance that a civilization might send another message. Instead, the prevailing strategy involves conducting broad surveys of the sky, covering as much celestial territory as possible in the hope of making a fortunate discovery. To draw an analogy, if the search were like fishing, instead of leaving a line in one promising spot for a long time, they are continuously casting their line into new areas, checking for an immediate bite, and moving on if they find nothing. This strategy is more sound than a simple analogy might suggest, as alien signals are not like fish that can be attracted by a lure or frightened away by the sudden attention of a telescope. And while a focused, methodical search has its merits, there is always a chance that a wide-ranging sweep will happen upon some form of evidence. The real difficulty arises in the follow-up. Over the years, radio telescopes have detected numerous other anomalies similar to the WOW signal, strange, unexplained bursts of energy. But because our approach does not prioritize focusing on these events with sustained, long-term study, a great deal of potential information is lost. As a result, we are often left with inconclusive findings. This brings us to a final reflection. It leads to the compelling possibility that our apparent solitude in the cosmos is not a reflection of reality, but rather a consequence of the very methods we employ to search for others. Of course, these ideas represent only a few of the many potential theories. For this exploration, the focus has been on some of the technical limitations that constrain our search for signs of alien life. Yet, there are other, more theoretical explanations that rely more heavily on speculation. These alternative ideas are fascinating in their own right and offer intriguing insights into our own civilization. If this subject has captured your interest, I will delve into those concepts in another video. The question of whether we are alone in the cosmos is a profound one, and it naturally leads to another. If intelligent life is out there, why has there been no contact? The search for such life is an immense challenge, primarily because of the ambiguity of what we might find. How would we truly know if an extraterrestrial civilization existed? An obvious confirmation would involve a direct visit to our planet on a global scale. One could picture immense vessels materializing over every major city on Earth, or perhaps a more diplomatic encounter, with emissaries meeting world leaders in a moment broadcast for all to see. It is also possible to imagine a future where interstellar trade introduces alien technologies and materials into our daily lives. Yet, whether for good or ill, there is little credible evidence that any of these scenarios has ever taken place. While a physical visit from another species would be an unmistakable sign, it is not the only way their existence could be revealed. A far more plausible method of discovery involves detecting their signals from across the vastness of space. Much discussion has centered on the potential reasons for an apparent cosmic silence. But it is worth exploring the opposite perspective. What are the most compelling pieces of evidence suggesting that we may have already intercepted a message? Among the many anomalous signals recorded over the years, which ones stand out as the best candidates for a genuine transmission from an alien world? Before examining them, it is important to acknowledge the inherent uncertainty in this search. The very concept of alien implies a profound otherness. We cannot be certain what to expect from beings that have likely evolved under entirely different conditions than our own. Their cultural perspectives, while perfectly logical to them, could be completely inscrutable to us. Consequently, their idea of a sensible way to announce their presence to the universe might differ radically from ours. Researchers scanning the skies for extraterrestrial transmissions must therefore maintain an open mind about what form a signal might take. This very open-mindedness, however, creates a significant problem. A potential alien signal could be easily confused with emissions from natural sources that we do not yet fully comprehend. The challenge lies in learning how to distinguish one from the other. A few key examples help illustrate this difficulty. In 2019, the Parkes Murayang telescope in Australia was being used for the Breakthrough Listen initiative. Its objective was to observe Proxima Centauri, the star system closest to our own, to gather data on the behavior of stellar flares. It was only later, when researchers with the Search for Extraterrestrial Intelligence, or SETI, analyzed the collected data, that they noticed something highly unusual. It was a signal that would come to be known as BLC-1. The discovery raised a tantalizing question. Could our nearest stellar neighbor actually host an advanced civilization? The signal itself was fascinating because it defied easy explanation by conventional sources. It persisted for several hours, a duration much longer than the typical time it takes for a human-made satellite to pass through a telescope's field of view. The transmission also exhibited signal drift. Its frequency was observed to be shifting, which suggested it was coming from a source that was moving relative to the telescope. This characteristic made it unlikely that the signal was caused by stationary interference on Earth. Perhaps the most compelling feature of BLC-1 was its extremely narrow bandwidth. In nature, radio emissions are almost always spread across a wide range of frequencies. They fluctuate broadly. Barring the existence of some undiscovered natural phenomenon, only one thing is known to produce such a focused and concise transmission: technology, whether of human or non-human origin. With no obvious human-made source to account for its existence, scientists naturally began to wonder if this could finally be the message from an alien intelligence they had long been searching for. Alongside the famous WOW signal, BLC-1 is considered one of the most promising candidates for a signal potentially created by an extraterrestrial civilization. And yet, even this remarkable signal is not without its problems. While researchers could not definitively link it to any specific source of technological interference on our planet, a deeper analysis of the data revealed a complication. The signal's signature closely matched other radio wave patterns that had been recorded on different days during the observation period. The critical issue was that these other, similar signals appeared no matter which direction the telescope was aimed. Furthermore, subsequent observations of Proxima Centauri failed to redetect BLC-1. So, while the precise cause of the interference that produced the BLC-1 signal remains a mystery, the probability that it was indeed interference is considered to be very high. Let us consider another candidate, the signal designated SHGB02+14a. When Frank Drake initiated one of the very first SETI experiments, Project OSMA, back in 1960, he began with a foundational premise. He reasoned that if an alien species wanted to communicate across the galaxy, they would likely choose the frequency of 1420 MHz. His logic was that this is the frequency naturally emitted by hydrogen, which is one of the most abundant elements throughout the universe. Drake theorized that any intelligent beings looking to make contact might use this specific frequency as a kind of universal common ground, a wavelength that would likely have special significance for any scientifically advanced race. This was perhaps a speculative leap, but it certainly made the later discovery of SHGB02+14 a particularly interesting, because this signal was broadcasting at that exact wavelength. The signal, which we can call SHG for simplicity, was detected on 3 separate occasions in 2003. The detection was made using the Arecibo telescope and leveraged the processing capabilities of 5.2 million home computers through the SETI at Home initiative, a fascinating program that is unfortunately no longer active. SHG had no clear natural explanation for its origin, and it did not appear to be simple interference. At the same time, the signal was too weak for scientists to be certain that it was clearly technological in nature. Adding to the mystery was its peculiar location. It seemed to originate from a point in space that was devoid of any stars for at least 1,000 light-years from Earth. And although the signal did exhibit drift, it did so in a way that raised suspicion among researchers. If a signal is being broadcast from a planet, there are certain characteristics one would expect to observe. A transmission coming from a planet's surface or from an object in orbit around it would likely show a specific Doppler shift, as its circular path caused it to alternate between moving toward us and away from us. There would also be periods where the signal would disappear entirely as the source moved behind its planet from our perspective. While SHG did show a fluctuation in its frequency, which varied between 8 and 37 Hz per second, this rate of change presented a problem. Such a rapid drift could only be produced by a planet that was rotating approximately 40 times faster than Earth, a scenario that seemed highly improbable. Another peculiar characteristic of the signal was its consistent starting frequency. What stood out was that no matter where it had last been observed in the sky, each new detection always began at precisely 1420 MHz. For this to be explained by a transmitter in orbit, an observer would need to catch it at the exact same point in its path on 3 separate occasions. This represents a scenario of extremely low probability. This recurring detail therefore strongly suggested that the SHG signal was more likely an instrumental artifact. It was probably some form of technological glitch within the equipment itself. The methodical evaluation of signals like BLC-1 and SHG provides a fascinating look into the process SETI employs to assess potential extraterrestrial communications. This entire approach seems to align perfectly with a principle famously articulated by Sir Arthur Conan Doyle through his detective, Sherlock Holmes. The core idea is that after you have methodically eliminated every impossible explanation, whatever is left must be the truth, no matter how improbable it might appear. Each time researchers identify a new signal of interest, they begin this process of elimination. They systematically rule out all known alternatives. They first investigate whether it could be interference generated by a passing satellite. They then question if any known natural process in the universe could be responsible for producing such an effect. They meticulously seek any other way to account for why the signal is present and why it is behaving in its specific manner. Thus far, alternative explanations have been successfully found for all leading contenders for alien communication. Even in cases where human-made interference can be completely ruled out, a compelling possibility remains. These enigmatic signals could simply be undiscovered natural phenomena. This very line of reasoning is central to the current discussion about the final candidate for an alien signal we will explore: fast radio bursts. If a distant civilization were ever detected, the discovery might not come from an intentional message at all. It is possible that powerful technologies, such as massive engines activating or focused energy beams firing, could release immense bursts of energy. These bursts could inadvertently reveal a galactic civilization's presence. This is precisely what makes fast radio bursts, or FRBs, so compelling. As their name suggests, they are incredibly rapid, powerful bursts of radio waves. Astronomers have now catalogued hundreds of these strange, millisecond-long events appearing from all directions in the sky. Some scientists even theorize that thousands of them might be occurring across the cosmos every single day. The vast majority have been detected originating from far outside our own galaxy. However, one was observed within the Milky Way in 2020, confirming they are not entirely foreign to our cosmic neighborhood. The signals appear to emanate from sources with extraordinarily powerful magnetic fields. As of now, scientists have no definitive explanation for what might cause them. A variety of theories exist, of course. Perhaps they are emitted by neutron stars, or maybe even black holes. Yet there is no conclusive proof that places any single theory above another, and this includes the hypothesis of alien technology. In Canada, the CHIME telescope possesses a unique design that makes it exceptionally well suited for detecting these fleeting cosmic blips. It cleverly avoids the limitations of many other telescopes. Instead of focusing on a single point in space, CHIME's multiple cylindrical parabolic reflectors can gather data from an entire swath of the sky at once. It began its observations in 2018 and continues its important work to this day. The telescope has successfully detected FRBs that repeat their signals. It has also found one that is definitively associated with a magnetar star. It is possible that all FRBs can be linked to such stars, but it is also possible they cannot, and that is precisely the point of the mystery. Perhaps one day we will be able to identify the origin of all FRBs. We might confirm they have a perfectly natural source. In that case, the search for alien life would have to begin anew. But there is always that tantalizing hope, that slender possibility. One day, a scientist may rule out signal after signal until one finally arrives that defies every alternative explanation. If all other possibilities can be confidently ruled out, allowing us to say for certain that no natural source caused the signal, then we will be left with the wisdom of the great detective. We will have no choice but to accept the improbable. So, while these represent some of the best candidates for signals from another world, even they have significant arguments against them. We have not yet discovered a signal that points conclusively to the existence of extraterrestrial life, but this is not to say that we never will. The prevailing wisdom is that it is never aliens, a belief that holds true only until the moment it is proven not to be. About 800 light-years away, an unseen antimatter factory is churning out high-energy positrons. These minute particles of antimatter are streaming through the cosmos and colliding with our planet. For most of history, we were entirely unaware that this strange source even existed. The majority of the positrons bombarding Earth went completely undetected. They were simply absorbed by our planet's protective atmosphere. It was not until we began looking from a vantage point beyond the confines of our world that we started to notice them. In 2011, aboard the International Space Station some 200 meters up, NASA's Alpha Magnetic Spectrometer was switched on. This state-of-the-art particle detector immediately began to find positrons. The presence of these subatomic particles was certainly expected, but what was unexpected were the quantities being observed. The sheer volume of positrons being detected was so great that conventional sources, like natural radioactive decay and cosmic rays, could no longer offer a sufficient explanation. This raised the critical question of where they were all coming from. We have only recently been able to trace the culprit behind this cosmic antimatter shower. The solution, it turns out, is connected to another high-energy discovery, a strange gamma-ray haze named Geminga, which was first identified back in the 1970s. What is this mysterious source of gamma radiation, and what is its connection to the unusual abundance of high-energy positrons striking our planet? High in our night sky, nestled within the Gemini constellation in the northern celestial hemisphere, something peculiar is happening. In 1972, NASA's Small Astronomy Satellite 2, or SAS-2, identified an unknown source of gamma radiation. With the technology available at the time, however, the best it could do was trace the origin to a wider region of our Milky Way. Consequently, the radiation's ultimate source remained hidden among the stars for decades. Nevertheless, it was given a name. It was called Geminga, a name coined in 1976 by Italian physicist Giovanni Bignami, who would dedicate his career to studying it. The name is a clever play on words, a combination of Gemini, the region where it is located, and gamma, the type of radiation it emits. Intriguingly, Geminga is also a pun in Bignami's Milanese dialect, meaning it's not there. This was a perfectly fitting name for a gamma-ray haze with such an unknown origin. It was not until 1983 that Bignami and his team finally achieved their major breakthrough. A faint X-ray signature from Geminga was detected with the Einstein X-ray satellite, and while the source's precise location was still a mystery, this discovery helped to constrain the search field, bringing scientists closer to pinpointing its position. The fundamental question of what Geminga actually was, however, remained unanswered, leaving astronomers with only tentative hypotheses about its identity. This was the situation until 1991, when a significant breakthrough occurred. 2 independent space missions detected radiation from Geminga that was not steady, but pulsed. The initial discovery came from a German-made X-ray telescope called ROSAT, an abbreviation for Röntgen satellite, which is named for the German term for X-rays. ROSAT was the first instrument to register pulses in the X-ray emissions from Geminga, and shortly thereafter, these pulses were also verified in gamma-ray wavelengths by the Energetic Gamma-Ray Experiment Telescope, or EGRET, an instrument on NASA's Compton Gamma-Ray Observatory satellite. These complementary findings did more than just confirm that both the X-rays and gamma-rays originated from the same source. For the very first time, they unveiled Geminga's true nature. The object was flashing with a period of 0.237 seconds as it rotated on its axis, a rate of just over 4 Hz, or 4 times every second. This behavior was the unmistakable signature of a pulsar. A pulsar is a rapidly rotating neutron star that projects beams of radiation into space, sweeping past our line of sight like the beam of a celestial lighthouse. Viewed from Earth, the majority of pulsars seem to blink in radio wavelengths, with frequencies ranging from a few times a minute up to a remarkable 700 times per second. In the early 1990s, however, pulsars detected in high-energy gamma rays were exceptionally uncommon. Before the observations from ROSAT and EGRET, only 2 such objects had ever been found: the Crab and Vela pulsars. Yet, the Crab and Vela pulsars differed from Geminga in 2 significant respects. First, both of those objects emitted radio waves in addition to gamma rays, making them detectable by radio telescopes. If Geminga was indeed a pulsar, it represented the first of its kind to be seemingly radio quiet, radiating only enough energy to be observed in the gamma ray and X-ray portions of the spectrum. The second key difference was that both Crab and Vela are enveloped in nebulae, the leftover material from the supernova explosions that formed them. Geminga, by contrast, had no visible nebula. This absence was puzzling. What accounted for Geminga, this potent gamma-ray source, being so elusive to radio astronomy? What had happened to its nebula? Or was it possible that it was not a pulsar at all, but some other kind of celestial object? The solution to the first mystery, it turns out, was partly that we had not been observing in the right way, a consequence of both the technological constraints of the era and our incomplete knowledge of radio emissions from these kinds of stellar remnants. Radio pulsars can broadcast across a vast bandwidth, from as low as 17 MHz to over 87 GHz, covering about half the radio spectrum. However, not all of these frequencies propagate efficiently through the cosmos. Scientists had known since the 1970s that radio pulsars are often at their most intrinsically luminous, between 100 and 200 MHz. But factors such as the interstellar medium, the ambient temperature of the sky, and distortions from the ionosphere all conspire to attenuate these lower frequencies during their journey across space. The result is an extremely faint signal that is profoundly challenging to detect. Given the weakness of these radio signals, the majority of radio telescopes had not been designed to search for them. Their efforts instead concentrated on a frequency range between 430 and 1,600 MGHz. This approach would have been sufficient if Geminga had behaved like a typical pulsar of its type, but it did not, and it was not until 1997 that researchers understood the situation. Using a sensitive transit antenna, 3 separate observations from the Pushchino Radio Astronomy Observatory successfully detected incredibly faint pulses from Geminga. These weak radio signals were centered around 100 megahertzes, finally explaining why earlier radio surveys had found nothing. It became clear that Geminga was not truly hidden. It had been transmitting signals all along, but we had simply been tuned to the wrong frequencies. Also, in 1997, a group of scientists headed by the late astronomer Janusz Gill proposed an additional explanation for Geminga's apparent radio silence, suggesting its magnetic field was a contributing factor. Their models indicated that radio waves could be absorbed or bent within the pulsar's magnetosphere. This process would leave only feeble pulses around 100 megahertz able to escape and be detected, rendering the object silent at the higher radio frequencies used by most observatories. The confirmation of Geminga as a pulsar, and more specifically a gamma-ray pulsar, was a momentous achievement. An astonishing 99% of its total energy output is in the form of gamma rays, which establishes it as one of the most luminous gamma-ray sources in the Milky Way. We now understand that it is the surviving core of a star several times more massive than our Sun, which detonated in a supernova approximately 350,000 years ago. Yet, its near-total radio silence and the absence of a visible nebula were not the only peculiar characteristics of this pulsar. By comparing a set of observations from the European Southern Observatory's 6 meters telescope and New Technology telescope, with data from the Canada-France-Hawaii telescope, Italian astrophysicists, including Geminga's discoverer Giovanni Bignami, made another discovery. They determined that Geminga was in motion. More than that, it was traversing the sky at a remarkably high velocity of about 0.2 arcseconds per year. To put this into perspective, an arcsecond is an extremely small unit of angular measure, employed when precision beyond what a degree can offer is required. Each degree of arc is subdivided into 60 arc minutes, and each of those arc minutes contains 60 arc seconds. This unit, the arcsecond, is commonly used in astronomy to describe the apparent motion of celestial objects across the sky, as seen from our vantage point on Earth. Imagine a complete circle drawn around the sky. This circle encompasses 360 degrees. At any given moment, with an unobstructed view, about 180 degrees of the sky are visible from horizon to horizon. The distance from the horizon straight up to the zenith, the point directly overhead, measures 90 degrees. A simple way to visualize this is to hold your little finger out at arm's length. With one eye closed, the width of your fingertip will cover approximately 1 degree of the sky. On a clear night, you can test this by seeing if your finger can obscure the moon. It should, as the moon itself spans only about half a degree, or roughly 31 arc minutes, of the night sky. While Geminga's movement of 0.2 arc seconds across our sky annually might not seem substantial, it is quite significant when compared to the motion of an average star. From our perspective here on Earth, a typical star shifts its position by only a few thousandths of an arc second each year. Even from its distance of 800 light-years, Geminga's movement across the cosmos is perceptible. Over a span of just over 10,000 years, it will traverse a section of our sky equal to 30 arc minutes, a distance that matches the apparent width of the full moon. This stellar remnant is hurtling through the galaxy at an astonishing speed of nearly 210 kilometers per second. Its trajectory is carrying it toward the boundary between the constellations of Gemini and Lynx. Based on its current path and velocity, Geminga is expected to reside within Gemini for another 500,000 years, after which it might warrant a new designation. This immense speed, however, is connected to another of the pulsar's remarkable features, one that researchers were on the verge of uncovering. As Geminga plows through space, it leaves in its wake 2 ethereal tails of X-ray emissions that extend for 3 trillion kilometers. And while this rapidly moving pulsar is almost completely silent in the radio spectrum, it is anything but quiet when observed in gamma-ray and X-ray wavelengths. In 1999, the European Space Agency launched its X-ray multi-mirror mission, or XMM Newton, designed to explore the universe in these higher energies. Just 4 years after its launch, a research group headed by Patrizia Caraveo revealed the existence of these comet-like X-ray trails. The shape and luminosity of the tails can be partially attributed to the shockwave generated by Geminga's forward motion and its spin as a pulsar. Yet, they also pointed to another fundamental quality: Geminga's tremendous mass. Despite being only 20 to 30 kilometers in diameter, Geminga is incredibly dense, packing the mass of about 1.5 of our own suns into its small volume. To grasp this density, consider that a single teaspoon of material from a neutron star would have a weight of approximately 4 billion tons, equivalent to 10,000 Empire State Buildings. As this compact, high-mass body speeds through the diffuse interstellar medium, which has a density of just 0.06 to 0.15 atoms per cubic centimeter, it creates a compression effect. The medium and the magnetic field embedded within it are compressed by a factor of 4. At the same time, the neutron star's relentless rotation forges an environment where electrons and their antimatter counterparts, known as positrons, are accelerated to incredible energies. These energies are sufficient to produce high-energy gamma rays. While the majority of these electrons escape as the gamma radiation we detect from the pulsar, a portion becomes ensnared, spiraling inside this intensified magnetic field. Computer simulations illustrate how these tails stream along the boundaries of Geminga's three-dimensional shockwave. The phenomenon is reminiscent of the wake left by a boat moving through water. The key difference, of course, is that this particular boat is more massive than our Sun, and its wake is composed of exceptionally high-energy X-rays. The last major component of the Geminga mystery, however, was not resolved until 2005 with the discovery of its nebula. This structure appeared as a shell of neutral hydrogen gas, measuring 0.4 parsecs in radius. It was identified as what is known as a pulsar wind nebula. Nebulae of this kind are formed by the plasma wind that flows from a pulsar's magnetic poles. This plasma, consisting of charged particles accelerated to nearly the speed of light, envelops the pulsar and forms a nebula of high-energy particles that produce powerful X-ray emissions. The confirmation that Geminga possessed a nebula finally solidified its classification as a pulsar, but the Chandra X-ray Observatory provided even deeper insights. In addition to creating images of Geminga, Chandra also observed a different pulsar, designated B355+54. By comparing the two objects, astronomers developed a potential new explanation for why Geminga lacks significant radio pulses. At first glance, the two pulsars appear remarkably similar. Both are estimated to be around 500,000 years old, and each one rotates about 4 to 5 times every second. The crucial distinction is that Geminga is predominantly observed through its gamma-ray pulses, with no bright radio signature. In stark contrast, the second pulsar, which we can call pulsar B, is not detected in gamma rays at all. Instead, it is one of the most luminous radio pulsars ever found. The question then becomes how two such similar pulsars could present themselves so differently to our instruments. The solution may be as straightforward as their geometric orientation with respect to our line of sight from Earth. Scientists propose that the images of Geminga and pulsar B have offered a glimpse of their respective spin axes, thereby revealing a reason why radio and gamma-ray pulses might be visible from some pulsars but not others. Much like the magnetic field of our own planet, both of these pulsars possess magnetic poles situated close to their rotational poles. It is from these magnetic poles that the focused beams of pulsing radio emissions originate. One way to visualize this is to imagine a small foam ball representing the pulsar, pierced directly through its center by a skewer. The skewer, emerging from both ends, stands in for the radio beams that emanate from the poles. If you were to spin the ball around this skewer, which acts as the spin axis, you would establish an equator around its middle. To represent the source of gamma rays, which radiate from a torus along this spin equator, you could fit a paper plate with a hole in its center over the foam ball. This creates a model with a disk of gamma rays shining outward from the equator in all directions. In the case of Geminga, the edge of this paper plate disk is aimed toward us, which means the gamma rays are directed toward Earth. For pulsar B, however, its orientation relative to us is at a different angle, as if we were viewing the flat face of the plate. Consequently, its gamma rays travel perpendicular to our line of sight, completely missing our planet. Revisiting the two Chandra images, with Jaminga on the left and Pulsar B on the right, alongside artists' concepts of their pulsar wind nebulae, helps clarify this idea. In the depiction of Pulsar B, the long, trailing blue structures are the radio jets streaming from its poles. But because Pulsar B is moving so quickly, these jets are not straight. They appear swept back, trailing behind the pulsar on its journey. Now, observing the image of Jaminga, we see that the long twin tails on either side are also radio jets trailing behind it as it speeds through space. The critical difference is that instead of being pointed nearly toward and away from our position on Earth, these jets seem to be projected off to the sides and are not aimed in our direction. Therefore, when astronomers observe Jaminga, they detect the powerful gamma-ray emissions from its spin equator, while its radio jets are angled to the side and go unseen. Conversely, when they observe Pulsar B, the situation is reversed. Its radio jets are pointed almost directly at our world, but the gamma-ray source at its equator is oriented in a way that its emissions bypass Earth entirely. It seems that sometimes the simplest explanation holds the key. This understanding finally allows us to return to the decades-long puzzle of an anomalous excess of antimatter reaching our planet. For well over a decade, the International Space Station has served as the orbital home for a sophisticated particle detector known as the Alpha Magnetic Spectrometer, or AMS-2. Its ongoing mission is to gather data on the universe's most elusive components, including antimatter, dark matter, and the origins of cosmic rays. Cosmic rays, it's worth remembering, are immensely energetic particles, essentially the fragments of atoms that traverse the vastness of space at velocities approaching the speed of light. Their genesis can be traced to various cosmic phenomena, such as our own sun, powerful supernova explosions, and other energetic events throughout the cosmos. The year 2013 marked a significant milestone when the first results from the AMS-2 experiment were publicly shared. The instrument had successfully registered more than 400,000 positrons, which constituted the most substantial sample of cosmic ray positron data ever compiled. This single achievement effectively increased the world's entire repository of such data by a factor of 100. For many years, a considerable number of astronomers and physicists held on to the hope that this observed surplus of antimatter might be the signature byproduct of dark matter annihilation. Such a discovery would have offered invaluable clues regarding this profoundly mysterious substance. After all, current models suggest that dark matter could constitute approximately 27% of the entire universe. Despite its prevalence, we remain fundamentally uncertain about its true nature. Much like ordinary matter, dark matter possesses mass and occupies volume. However, a key distinction is that it does not appear to absorb, reflect, or engage with light in any manner that our instruments can currently perceive. Some scientific theories propose that dark matter could be composed of as yet undiscovered particle types. Whatever its ultimate composition, researchers had harbored high expectations that the overabundance of antimatter detected from the ISS could unlock secrets about dark matter's fundamental properties. Unfortunately, these hopes have gradually given way to a different reality. As scientists delve deeper into the accumulated data, a clearer and perhaps more mundane picture is emerging. The most probable origin for these positrons appears to be a class of celestial objects known as pulsars. This possibility had long been suspected by astrophysicists, but a lack of concrete proof persisted until 2017. It was the high-altitude water Cherenkov Gamma Ray Observatory that finally supplied the critical evidence needed to bolster this hypothesis. A compact halo of gamma radiation was identified in the vicinity of a pulsar named Jaminga, emitting energy trillions of times greater than what is visible to the human eye. This radiation measured between 5 and 40 trillion electron volts, a range typically associated with the activity of positrons. This observation represented the first genuine, tangible evidence that pointed toward a pulsar as a potential source for the detected antimatter. Pulsars, by their very nature, envelop themselves in a cloud of both electrons and their antimatter counterparts, positrons, a direct consequence of the star's incredibly powerful magnetic field. This intense field actively strips particles from the pulsar's surface, accelerating them to nearly the speed of light. Scientists theorize that these accelerated positrons and electrons then collide with ambient starlight, boosting the light's photons to much higher energies. This high-energy light is what subsequently radiates outward as the gamma-ray halo that was observed. However, based on the initial dimensions of the halo seen by the HOC team, it seemed that Geminga's positrons would seldom possess the requisite energy to travel all the way to our planet. Consequently, the team believed the excess positrons must originate from a more exotic source. This was the prevailing view until a remarkable new perspective was uncovered a few years later. The breakthrough came from a team headed by astrophysicist Matteo Di Mauro, which utilized a decade's worth of gamma-ray data on Geminga, acquired by Fermi's Large Area Telescope. This instrument has the advantage of being able to observe lower energy light compared to the Hawke Gamma Ray Observatory. Di Mauro's team meticulously processed the data, subtracting all other known gamma-ray sources to isolate the emissions from Geminga. What they revealed was an expansive luminescence emanating from the pulsar, far larger than what any scientist had previously documented. This vast, oblong halo of glowing gamma rays, measured at an energy of 10 billion electron volts, stretched across 20 degrees of the night sky, an area comparable to the celestial footprint of the Big Dipper constellation. And the discovery didn't end there. The glow of gamma radiation becomes even more immense at lower energy levels. If our eyes were capable of perceiving this entire spectacle, Geminga's gamma-ray glow would be a dominant feature in our sky, covering a region 40 times larger than the full moon. Armed with this new information, astrophysicists calculated that the sheer size of Geminga's halo meant that this one pulsar alone could be responsible for as much as 20% of the surplus positrons detected in Earth's vicinity. From this finding, it is not a significant leap to imagine that the remaining antimatter abundance is likely produced by the collective contribution of other, similar pulsars. While this explanation may not have unraveled the enigma of dark matter, it is undeniably a magnificent revelation in its own right. The history of these objects began when Jocelyn Bell discovered the very first pulsar in 1967, a time when some speculated that such regular, repeating signals could be evidence of extraterrestrial intelligence. In the nearly 6 decades that have passed since that initial finding, we have identified thousands of pulsars, and our comprehension of these dense neutron stars has expanded with each new one. And since Geminga itself was identified in 1991 as only the third known gamma-ray pulsar, our catalogue has grown to over 300, largely thanks to the efforts of NASA's Fermi mission. But considering Geminga's consistent record of defying scientific expectations and advancing our knowledge, it feels probable that this particular pulsar still holds more secrets, waiting to be revealed.